Hello and welcome to Pepperl+Fuchs 2013 Ultrasonic Sensor Basic Training. To cover everything that there is to know about Pepperl+Fuchs ultrasonic sensor line would take a tremendous amount of time. So what we've done for the basic training is boiled everything down to 6 basics that I think are, as product manager, the most important things to cover for learning, getting a good base for your ultrasonic sensor knowledge. We want to know, why would you choose an ultrasonic sensor? What are the operation principles behind how they work? Understanding sensor specifications, I think, is important, knowing how to use the catalog, knowing how to use the data sheets that are on our website. Model overview of probably what I would consider the most popular models, the accessories that are involved with these products, and then also some of the basic applications where an ultrasonic sensor would be applied. Before we get started, here's a couple little-known ultrasonic sensor facts that I think are important to know as we go forward with the training. First of all, in February of 2010, we acquired the sensor business from Siemens, and included in that business was their ultrasonic sensor product line. And that acquisition made Pepperl+Fuchs the #1 ultrasonic sensor manufacturer in the world. The U.S.'s largest single customer of ultrasonics uses thousands of ultrasonics annually. I think this is important to know because it seems sometimes like it's as opposed to inductives or photo eyes, maybe it's not such a mainstream product line. But people do use these products by the thousands in the United States and throughout the rest of the world. And maybe another interesting point to know is the all-time largest single sensor order ever in the history of P&F worldwide was an ultrasonic sensor order. So these are products that are very sellable and very universally used. I think the most important question to be asked as you start learning about ultrasonics is, why would someone choose to use an ultrasonic sensor? With all the different technologies out there of inductive, photo-wise, capacitive, magnetic, why would you choose ultrasonic sensors? Well, I think in the sensor selection chain of thought, the #1 option for any sensing application would probably be inductive. Inductive sensors are very inexpensive, great environmental immunity to liquids, oils, greases, sprays, whatever. Very, very durable product as well. But the negatives to these products, they have a very short range, typically less than 50 millimeters, and also the target must be metal. So if you're looking for maybe the level control of a liquid or grains or something like that, inductives aren't going to work for you. Well, if inductives aren't going to work, in my opinion, the next option would be optics or photo eyes. They're also somewhat inexpensive. They have a much longer sensing range, so if you're looking to see a target at something longer than 50 millimeters, at a meter, 2 meters, 100 meters, photo eyes are a good option for that. They're very precise and very fast. The negatives for a photo eye, the detection is color and opacity, which is the clarity, like whether it's glass or it's not see-through. It's opacity dependent. It's unusable in dirty environments. If that lens gets clouded up, it's like trying to take a picture with a dirty lens. It's just not going to work. And the ambient light interference, if you've got any kind of fluorescent lighting and things, sometimes those can wreak a little bit of havoc with optical sensors. So if inductives and optic sensors don't do the job, the next solution is going to be an ultrasonic sensor. And some of the positives about an ultrasonic sensor are the long sensing range. We have some models that go out to 34 feet, which is 10 meters. They're very reliable in dirty environments because it's sound, it's not optical. So there's no problem with dirt on the face. The sensors work great. There's many analog models, so if you need a continuous feedback of how close or far away something is, not just if it's on or off, there's a lot of options with ultrasonics. And target color and target reflectivity, like optical reflectivity, is irrelevant. Sensors work great whether the target's black or white or pink. Negatives to an ultrasonic, they are going to be a little more expensive, especially than inductives, and oftentimes a little bit more than photo eyes, but not the specialty photo eyes. So I think as opposed to, like, if you consider background suppression or clear object detection or some of the higher end photo eyes, then they're pretty much in the same ballpark as an ultrasonic. The response time for ultrasonics, because they rely on the speed of sound, is a little bit slower. So you need to make sure, look at your data sheet to make sure the response time of the ultrasonic you'd be looking at is suitable for an application. And also there's a wide sensing area, and that sometimes is a negative if you're trying to shoot through an area and detect a target in a very space-restricted area with a lot of obstructions. But it can also be an advantage if you want to get an average over a wide area or cover a wide area, like for collision avoidance or something like that. So those are the positives and potentially some of the drawbacks to ultrasonic sensors. Okay, next we're going to discuss the ultrasonic sensor operating principles. The first and probably most popular mode is diffused operation. In this mode, the sensor calculates the time elapsed from when it emits a sound pulse and when the echo pulse returns. And it uses the speed of sound to do that. So it knows that the speed of sound travels at 1,128 feet per second. So by sending out a pulse and calculating the time it took for that pulse to come back, it can tell how close or far away something is. You can see that in the first application example in the top right corner, where a lot of today's vehicles have ultrasonic sensors embedded in the bumpers. And you can tell by the quickness of the beeps as you get closer to something like a tricycle that's behind the vehicle, it'll go beep, 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 and then beep, 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 beep. Beeps a lot faster the closer you get. It's using the speed of sound to detect how close or far away that tricycle is. The other modes that are kind of more application solvers are Thru-Beam. So you can see with the bottles coming down that line, the clear bottles on the bottom right-hand corner. Typically that's going to be a Thru-Beam application. And there's also a retroreflective mode. So just like a photo eye looks at a reflector, the ultrasonic can look at a target object or a flat panel or something and use that as a reflector, and as an object comes past, it breaks the beam, and you have an ultrasonic retroreflective sensor. So those are the three operating principles used by ultrasonic sensors. When you look at an ultrasonic sensor data sheet, you'll see a lot of terminology: resolution, analog, blind zone, temperature compensation, synchronization, beam angle. There's a lot of different specifications that are unique to ultrasonic sensors. So in section number 3, we're going to discuss what some of the most important ones mean. When you first look at a product data sheet, you're going to be looking probably for a model number. And quickly, I want to go over the product nomenclature for ultrasonic sensors, which is very easy, because if you've looked at any of the inductive or photoelectric or any of the other options from Pepperl+Fuchs, the ultrasonic sensor follows the same basic structure. So the UB would mean ultrasonic. If we're looking again at this sensor model down at the bottom, UB1000, 18GM, 75, I, V15. So the 1000 is the sensing range, the 18 is the diameter, the 75 is the length, I is universal, whether it's an analog or a photo eye, or that means it's an analog output. And then the connector. These use the same type of connectors for all, as all of Pepperl+Fuchs sensors use. So in V15 is a 5-pin micro quick disconnect. So that's a quick look at the nomenclature, but if you know the inductive nomenclature, you pretty much automatically know the ultrasonic nomenclature. Okay. Now we're going to take a look at the specifications as they relate to the data sheet, because the data sheet is the key. That's what you're going to get all your information from. That's what your customer is going to get all his information from. So you can see on the right a screen capture of a data sheet that was pulled from our website, and you can find the sensor performance specifications, the electrical data and dimensional drawings, the product features, programming instructions, and also a series of recommended accessories. So everything you need to know if this ultrasonic sensor would be right for you is contained in the data sheet. When a customer is choosing a ultrasonic sensor, probably the first thing he's going to ask or want to know is, what's the sensing range? If you're a sensor, if you're looking for a sensor, you want to know how far away could it detect a product. And the sensing range, there's two different specifications that involve the sensing range. One is the actual sensing range, which is the maximum usable sensing area. And the next is the adjustment range, which is our maximum recommended sensing limits. So for this UB800 model, if you look at the sensing range is actually 50 to 800, but the adjustment range that we recommend is 70 to 800. And we do that because 50 is the near limit. If you get any closer than 50 millimeters to the transducer, you penetrate what is called the unusable area. And in that area, you can have some instabilities to your output. So we recommend that you get a little further away for your near distance so that you don't get into that area and have any stability issues. And we'll talk about the unusable area next. The unusable area is also called by some manufacturers the dead band or the blind zone, but it's an area where target placement or sensor programming is not allowed. The output can be unpredictable in this window, and what happens is the way the sensor works, it sends out an ultrasonic pulse and it waits for it to come back, and there's a ringing involved. And that sensor needs to stop ringing, the transducer needs to stop ringing so it can accurately hear the echo return. And if you're too close, the sensor transducer is still vibrating and it's going to have some stability issues and not be able to hear that echo pulse return. So here's kind of a graphical illustration and maybe a oscilloscope illustration of what's going on when an ultrasonic sensor transducer is struck and creates its evaluation pulse. The transducer, as I mentioned in the previous slide, must settle before it receives an echo. So you have that area where it's just really too close. The sound comes out, hits a target, comes back to the transducer while it's still ringing, and it can't determine what's going on because it needs to settle before it can listen. It is the user's responsibility to configure the sensor within the correct limits. The sensor won't know if you're in the blind zone or not because it's still ringing. It has no idea what's going on. You can get multiple echoes where the sound pulse goes from the transducer to the target, back to the transducer, back to the target, and back. And in that period of time, the transducer will have finally settled down and it thinks the target's twice as far away as it really is. So the sensor doesn't know. If it's in the blind zone, all bets are off. So the customer must know there's just no way that he should be banking on using that blind zone area for his detection. You've got to be from the end of the blind zone out. Now with the Thru-Beam model, so we were discussing a diffused model before, there is very much a minimal blind zone because now you have a dedicated emitter and a dedicated receiver. So it's constantly, the emitter is constantly sending out, the receiver is constantly listening. And that allows for a very small, if non-existent, deadband. So you can see here, you've got a 1 meter, 1,000 millimeter sensing range, but you can put these as close as 15 millimeters apart and still have a nice strong signal between them with no issues as far as ringing and multiple reflections and things. You can also see here the switching frequency of an ultrasonic Thru-Beam here is 1,000 hertz for this model. If you were to have the equivalent model for a diffused version, it would probably be around 10 hertz or 15 hertz. So you can see by not having to wait for that emitter transducer to settle and listen, you can go a lot faster. It's a continuous stream of sending and receiving. So it's this Thru-Beam ultrasonic, or the Thru-Beam mode, is the fastest available response time for ultrasonic sensors. The next topic to discuss is the beam angle. Just like as if you were to talk, your voice kind of fills the entire room as you speak. Ultrasonic sensors are also using sound, so their sound expands out in kind of a conical shape once that transducer is struck and the evaluation pulse is created. So that's something to keep in mind, is that it's not like a laser beam, that the sound does come out in a wider area and you have a wider area of coverage for ultrasonics. And this beam angle is specified in Pepperl+Fuchs datasheets. Okay, here's a screen capture of a characteristic response curve that's found in any ultrasonic sensor's datasheet. And you can see that the beam angle is going to be dependent upon the target. So you've got curve number 1, or area coverage number 1, and area coverage number 2. Number 1 is a 100 millimeter by 100 millimeter flat plate. So a very 4-inch square wide plate. This curve 2 is in response to a 25 millimeter or a 1-inch diameter rod or round bar. So you can see, if it's a flat plate, you can detect it much further away and in a much wider area than if it's a rounded target, which is much less reflective, and also it's smaller. So the beam angle is dependent upon the target size, the contour, whether it's flat and much more reflective, or round where some of the sound disperses when it hits and doesn't come straight back to the sensor. It's dependent upon the alignment, how perpendicular it is to the target. And also the density. If it's something soft like a felt or a foam or something, it's going to be much more difficult to detect than if it's a nice, hard, acoustically reflective part. And also of note is sometimes the beam angle can be customized by software or by configuration wires. And that's something, when we talk about software customization, we'll be covering that a little bit in our intermediate and advanced classes. That's not something we're going to cover in depth in the basic classes. We're going to discuss the beam angle and the target relationship a little more in detail on this particular slide. Highly reflective targets can be detected quite a ways beyond what the nominal specification is in our catalog. So a UB800, for example, which is what this technical data screenshot is taken from, you would think it could only go to 800 millimeters, but if the target's reflective enough, like this 100 by 100 or 4-inch square flat plate, you could actually see that plate out to 1200 millimeters with no problems. So there's a little excess gain built into ultrasonic sensor specifications. And you should be aware that a lot of competitors will not allow for this excess gain. They'll specify their sensor at the absolute maximum distance. So if you're doing a cross-reference for ultrasonic sensors versus one of our competitors, make sure that you look at their beam chart to see if their version of a UB800 really maximum is 800 or if it goes out to 1200. Sometimes the cross-references can be a little tricky because of the way different manufacturers specify their sensing ranges. Okay, we've talked a little bit about the specific standard targets that are used to measure an ultrasonics sensing range, 1-inch diameter rod and the 100 by 100 millimeter square metal plate. But in general, in real life, you aren't going to be using those targets. You're going to be using whatever you want to sense. So the best targets, as far as quality goes, are objects with a high density. So anything solid, liquids, granulars like rocks, like corn, whatever, like just things with a high density. And whether the target is perpendicular, that's obviously the best. You're getting the maximum sound back for your echo. And also rougher targets, as odd as that sounds, the rough targets, if you angle them left or right, you can get a lot wider sensing beam angle, and you don't have that issue where you have the sound deflecting off a smooth surface at an angle and not coming back to the sensor. So when that surface is rough, you still have some little corner cubes. It's kind of like bouncing a ball off the ground and into a wall and it comes back to you. When you have the rougher surfaces, you have a lot more of those corner cubes, and it's a lot better target than a very smooth, like a mirror or a smooth metal plate. Poor targets, felt, cloth, foam, rubber, frothy liquids, all of those absorb sound. So if you want a good reflective echo to come back, You want something that's going to reflect the sound very well, and soft targets, fluffy targets, cloth, things like that are not the best. It's not to say you can't detect them, but you've probably got to be quite a bit closer than you would something of a higher density. Smooth and angled targets I mentioned before, they can be detected, but again, you've either got to be a lot closer or you've got to make sure that you've got a perpendicular axis for your detection. And then very high surface temperatures. If you're looking at steel, molten steel, things like that, ultrasonics, that heat, that radiant heat that comes off of the product will diffuse the sound waves and pretty much render the product undetectable. For diffuse mode, Thru-Beam mode, it wouldn't matter. This slide illustrates what I spoke of on the previous slide regarding the angle that you can get away with when looking at a smooth target. Ideally, the target's going to be perpendicular, but that's not always possible in real life. So we'll allow up to a ±3 degree target variance, left or right, up and down, doesn't matter, where the target is still going to be detectable if the surface is like a mirror, like a glass, something very smooth. You can go beyond that to 10 degrees, 20 degrees, 30 degrees if it's a rougher surface. But the sound will, as you can see from the graphic with the incident ray and the reflected ray, if you're at a 45 degree angle, none of the sound on a smooth surface is going to come back. It's all going to be reflected off the other way, and the target would essentially be invisible. An application where this wider beam from an ultrasonic might be helpful is in overhead conveyors for collision avoidance. Because photo eyes, one area where photo eyes are sometimes used here is where you have the photo eye and then the reflector. And as long as you keep a reflector and the photo eye in a nice visual line, a nice linear line, it's no problem. You can see the reflector would be on the product in front and the emitter on the product behind it. And as long as they meet, then you know everything's going to be okay and you're not going to collide. You can gauge the distance that way. But the problem with that is as you make a turn, that reflector is not going to give you a good return path for your light. With the wider beam ultrasonic, and if you use like a rougher surface, like sandpaper, like some kind of the no-stick flooring that's used sometimes, it's very rough, or no-slip flooring, I should say. When you turn the corner, you get that 30, 40 degree plus minus that you have still no problems in maintaining the separation from vehicle to vehicle or device to device because you get that nice acoustic feedback from a rougher reflector. So it's nice to have that. Also, you don't care about the color. So if you're looking even at a car surface or something like that, clear color, black, white, doesn't matter with ultrasonics. An application tip, if I'll throw one out here, is that clear glass detection is a great application for ultrasonic sensors that photo eyes really tend to struggle with. So that's something to keep in mind with some companies. And in the automotives, we'll use the ultrasonic to adjust the window, moving it back and forth to make sure it's aligned during production so it seals nice. A little earlier in the presentation, we discussed response time of ultrasonic sensors and that they were a little bit slower than a photo eye or a little bit slower than inductives. If you look in the technical data sheet, you'll see a response delay specified for an ultrasonic, and this 800 millimeter range model you can see is about 100 milliseconds. Now that 100 milliseconds, what that tells you is the elapsed time from the sensor's pulse being emitted and the effect of its information that it gets returned on the output. So there's a little bit of a delay. It sends out its pulse, and then internal to the sensor, what it's really doing is it's probably going to take like 4 or 5 different pulses, successive, 1, 2, 3, 4, 5, and it's going to average them. So that way you get kind of your output doesn't jump up and down as it gets each echo back. It kind of averages those 5 out and then gives you the output, and that makes for a very smooth, stable output. So that's another reason why an inductive sensor or a photo eye might have a 1 or a 2 millisecond response time, and the ultrasonic is going to have 100. It's because it's taking multiple pulses, averaging them out, and then it's triggering the output to do whether it's analog, switch point, whatever the type of sensor is. One of the reasons an ultrasonic might use this averaging function is to improve the stability. So if you're looking at perhaps an agitated tank of whatever, water, beer, could be, whatever might be inside a tank, cleaning solutions, you're going to get peaks and valleys because that surface is going up and down. But you don't want your output to, you just want to basically know the average of the output. You don't want to know the peak and valley of every little wave and ripple. So that's one of the reasons why an ultrasonic sensor will average a series of echoes and then provide an output. It's to make for a smoother output in instances like level control. There's also some different, you can, through software, you can increase or decrease the amount of samplings that are taken to get a quicker response time, or if it's a very agitated tank or agitated surface, a longer sampling to smooth out an even more severe agitation. So again, we will probably in the intermediate and advanced sessions discuss how you can do that through computers. But something to keep in mind, if a sensor that's off the shelf is a little too unstable for a customer, you have the ability through software to customize the response time. And also, sometimes even without software, there are some methods to smooth out instabilities, and one is a stilling tube, where you can put the sensor inside a tube, and you can see that graphic on the bottom right, where it's kind of like a nice tranquil little island inside the tube. Because there's no waves in there, that the waves are on the outside, but the tube kind of stills everything. So stilling tubes are one method to get rid of widely deviating or fluctuating outputs due to an agitated surface. Customers are always going to be concerned with the accuracy of an ultrasonic product. That's one of the questions that comes up very frequently. And accuracy is the degree of overall correctness and precision of your device. So how close are you to being, if a target is 10 inches away, how accurate is your sensor going to be? Is it going to say it's exactly 10? Might it be 10.1? Might it be 9.5? That all depends on the accuracy. And the accuracy is not a single factor. It's a combination of, typically with ultrasonics, 3 factors. The resolution, the linearity, and the repeatability. And you can see in this highlighted excerpt from a data sheet below, you can see the resolution, the deviation from the characteristic curve, which is an analog thing, and then the repeatability or the repeat accuracy. So all those 3 components go together to create the accuracy spec. The next 2 concepts to discuss with ultrasonics as far as somewhat components of accuracy are the resolution and the repeatability. With resolution defines the smallest positional change that a sensor could recognize. So you can see on the graphic on the right, or the 2 graphics on the right, for low resolution, you get blocks, and you get a very blocky image. And that same kind of concept applies to an ultrasonic sensor, where maybe if you have an analog output that is 4 to 20 milliamps, if you have a 1 milliamp resolution, you would go 1 milliamp, and then you'd move until it jumps up to 2. Or I'm sorry, if you went 4 milliamps, it would jump up to 5, and then 5 jumps up to 6. If you have a higher resolution, then you can go 4 to 4.1, 4.1 to 4.2, 4.2 to 4.3, etc. So that's the difference in resolution. You get a much finer look the better the resolution is for a given product. Now, repeatability, that's a little different. The repeatability is the ability to reproduce a given result. So if you go one time out to a target that's 10 inches away, it tells you 10 inches. The next time you go out, it says 10.1. Then there's a 0.1 inch repeatability difference, or plus minus 0.5 inches. So you can look at the spec of in the data sheet and see that repeat accuracy or repeatability and find out from measurement to measurement how much you can vary. And the big component that makes that vary for an ultrasonic sensor is temperature change, because the speed of sound is temperature dependent. And some of the sensors will have a temperature compensation network that senses the ambient temperature and allows you a much greater degree of accuracy, because it's always giving the sensor feedback to the outside temperature. Some sensors that are very low end don't have that. But keep in mind then, repeatability repeatability is a component of primarily temperature changes. I'd mentioned before that temperature will affect the speed of sound. So let's look at a few of the other environmental influences that might affect the speed of sound. And this is important to know because these sensors are not always applied indoors in a nice climate-controlled factory. In fact, some of our largest customers are agricultural customers who use these things on crop sprayers and things like that. So they are used outdoors. Rain and snowfall in moderate amounts does not have any effect on an ultrasonic sensor's operation. Heavy rain, heavy snowfall, yes, that will affect an ultrasonic. Likewise, wind. Moderate amounts of wind have no effect on ultrasonic sensors operation, but I would not put them in a hurricane. The echo is going to get blown away, and the sensor will never see it. So moderate amounts of wind, no problem for an ultrasonic sensor. And also ambient noise. Now, back in the old days, in the early days of ultrasonic sensors, some of our competitors had little shiny metal transducers that you could jingle your car keys around or blow an air hose by, and they would immediately affect the output of a sensor. So some people, I think, if you've been around a long time, maybe they gave up on ultrasonics because of those problems. That's not really the case with our Pepperl+Fuchs ultrasonics. So those have a extremely high immunity to any kind of audible noise. They're on a different frequency, and it's coded. The sound is coded, so it's very difficult to have any effect, regardless of the decibel level, for ambient noise to affect our ultrasonics. A little more on environmental influences. Humidity. General outdoor humidity is not going to be a problem for any kind of ultrasonic sensor. The speed of sound may change a little bit, so your repeatability may change. But in general, these things are used outdoors all the time, so it's not really a too big of an effect. But if you're in a constantly steamy or constantly high humidity environment, that could be an issue. So you need if the sensor is exposed and over the course of a day gets its chance to dry out, or 2 days, you're not going to have a problem. But if you have like a steamy hot liquid and you have an ultrasonic that's constantly exposed to those vapors, that could be a problem over time. Dust and dirt, there's no effect. So you can see this agricultural machine on the top right corner. You almost can't see it through all the dust and dirt. But for the ground level that needed to be sensed on that machine, it's no problem at all. It's very, very accurate. And ambient temperature changes, mentioned that before. Changes in air temperature will affect the speed of sound and subsequently also affect the accuracy of your sensor a little bit. Here's a simple graphic that shows the temperature drift and the effects of having or not having temperature compensation. And this would be for a UB1000 model where the target would be at 1,000 millimeters. You can see at 1,000 millimeters and 68 degrees Fahrenheit, you get a 1,000 millimeter output. So that's the sensor knows exactly where the target's at. With the temperature compensation, you can still have a variance of about plus or minus 1.5%. So could go down to 985, could go up to 1,015, and that's more a component of the lag because the temperature compensation element is inside the sensor. So the outside temperature may change a little bit, and then the response of the sensor for compensating for that may lag a little bit just because it's kind of buried inside the sensor a little. You can also see here that as the temperature drops, the speed of sound slows down. So at minus 13 Fahrenheit on an uncompensated sensor, Since the speed of sound slows down, the sensor thinks the target might be further away. So there, where the deviance on an uncompensated sensor might be up to plus or minus 8.5% from the 1,000 millimeters, if the temperature is minus 13, it could conceivably think that the target is 1,077 millimeters away. If the environment is extremely hot, like 158 Fahrenheit, the speed of sound goes quicker, so the sensor thinks the target might be closer. So in that instance, 1,000 millimeters away, the sensor may think that the target's really 915 millimeters. But keep in mind, this is extremely worst case where we're, not too many areas go down to minus 13 Fahrenheit and up to 158 Fahrenheit. And also keep in mind that most of our sensors are temperature compensated, so we're in that smaller window and not the wider window. Okay, now we're moving along to the model and attribute overview. We know now the technology, we know about accuracy and temperature and all that kind of stuff. Now we're going to move into the models themselves, some of the more popular selling families of ultrasonic sensors that Pepperl+Fuchs offers. The two basic primary output types for ultrasonic sensors. There's switch point output, which is basic. Is the box there? Is the box not there? Is the level too high? Is the level low? And a lot of our sensors will have single or dual switch point outputs. So that's really the proximity mode. Works just like a proximity sensor. Is the target there? Is the target not there? Equally as popular for ultrasonics is the analog type. And here you get continuous feedback. So it's not just is the target there, is the target not there. It's giving you an increment. How close? Is it 4 millimeters away, 5 millimeters away, 6 millimeters away? So you get a continuous feedback. And that's either in an analog 4 to 20 milliamp or 0 to 10 volt output. And that can also be inverted. So some customers like it 20 to 4 and 10 to 0. You can do that as well. So we've discussed the UB300 and the UB1000, the UB800. So we're talking about all these different sensing ranges that are available. But size does matter for an ultrasonic transducer. So the bigger the drum, the more power, the further you can see a target. And the smaller, likewise, the smaller is going to be a smaller beam angle, higher frequency, and you've got to be a little bit closer in order to see the target. Okay, we're going to work our way up from cylindrical to surface mount and also from the smallest diameter to the largest diameter. So the first model I'm going to quickly highlight is the 12 millimeter diameter cylindrical version. And these models can be programmed either by a teach wire, where you touch the voltage to a plus or the minus when your target's at a given point and it stores it, or there's a push button programmer that you can plug into your power supply and thread into the back of the sensor, and you can push the buttons to learn the distances. The different models available are there's a 120 millimeter, a 200 millimeter, and then a 400 millimeter maximum sensing range version. And you get your analog current and voltage outputs as well as a PNP type. So you can take your pick of those three, which one you prefer. So moving up from our 12 millimeter diameter family to the 18 millimeter family, this is our half pint series. And we call it half pint because it's probably about half the size of the longer barrel model that we'll see in the next slide. So we've got a 40 millimeter barrel length, roughly the length of a matchstick. And you can go 300 millimeters and 800 millimeters. So by using that longer range version now, you can go with 800 longer than you could with any 12 millimeter model. So again, the bigger the drum, the more distance you get. There's a Thru-Beam option, there's analog current and voltage options, and it's also nice, you can see that the LEDs on this model are super big and super bright. So those can be something that customers really enjoy when they're doing their setup. Now we can take a look at the long barrel 18 millimeter diameter series. It's got a 75 millimeter barrel length as opposed to the 40 millimeter, but sometimes that's helpful. Sometimes, customers enjoy having a lot of extra mounting threads available. And in ultrasonic applications, a lot of times you have some space because you're looking at a target could be 1 feet, 2 feet, 34 feet away. Not for this model, obviously, but the mounting size of the transducer is sometimes not as critical, or oftentimes not as critical as it is for different sensors like capacitive or inductive. But moving on, again, this longer barrel 18 millimeter diameter series, same outputs as we've discussed before with analog and switch point, but it's also got a selectable beam width, which can be nice. So by taking the teach input for the beam selector, you can make for a wide beam or a skinny beam. So you can customize this sensor without the use of software for applications where you might need something with a beam that's a little tighter, a little wider. If a customer does need maximum range in a smaller space, it's a kind of a general rule that ultrasonics don't really have the space restrictions that an inductive needs, but it can certainly happen. So if you need high functionality and high power, we have remote transducers where the transducer element is all that's in the circular housing. And then maybe 1 meter away, you have the driver electronics mounted. So you can put that tiny little sensing head in a lot of space restrictive applications and then have the driver electronics located a yard away or 3 feet away. So it gives you some options that you couldn't get otherwise in the smaller barrel like the half pint size. Now you have software configurability, synchronization inputs. You can do a lot of things with these because you have so much microprocessor power inside that bigger barrel than you could get in a smaller one. So you get maximum performance and intelligence, but in the miniature design. Okay, this is kind of important to note that our 30 millimeter diameter plug programmable versions, if you're familiar with those, they have a socket in the back and a small plug that you could rotate, and you learn maybe one switch point and the end of your switch points to make a window, or the 4 milliamp and 20 milliamp components of an analog span. That family P&F has offered for probably over 15 years, and it is going to be obsoleted in favor of 2 new families. But it's not going to go away very quick, and I'm sure we'll keep it around for the next 3-5 years because there's such an installed base of it, and it's been a very popular series. So just something to keep in mind. I'm going to promote the next 2 families as the future, but this one that you may be familiar with if you've sold P&F for a little bit. If not, it's going to be around for the next several years, but will ultimately be replaced by the next 2 models. The first model that's going to replace the old plug series is our Series IO. And it has the identical sensing ranges as the plug versions, and I'll run those because I haven't discussed those yet. Run those past you as 500 millimeter, 2, 4, and 6 meter, 6 meter being roughly 20 feet, nominal sensing ranges. And these are kind of neat because instead of that plug that sometimes, if you're above a tank and you're plugging in your sensing range to learn your limits, you drop the plug in the tank. I would say a lot of people don't like that. These give you the same functionality, but with a push button. So they're very well sealed. There's no plug to come loose or fall off or drop. So that's the big feature of this product that will be a successor to the plug type, is it's all push button, nice membrane type push buttons that are very well sealed to the environment. They are configured either by the buttons, or if you want to go with the software, there's a program called Pactware that, again, if you take the intermediate and the advanced classes, you'll learn all about that. But you can do probably 90% of what you need with the buttons, and you don't need the software whatsoever. It's a nice product because they have push-pull outputs for switch points. Push-pull means they're NPN and PNP. So you don't need to stock 2 different models if somebody wants an NPN and somebody wants a PNP. And then the analog models also are both current and voltage. So that's a nice feature that you don't have to stock separate current or voltage models. And those ones also offer a switch point. And the LEDs on them are great. Very high visibility LEDs. There's 5 of them. And finally, it is IO-Link compatible. And IO-Link is a new sensor protocol. Again, an intermediate to advanced discussion to have on that. But if your customer asks you for an IO-Link compatible ultrasonic, now you've got a full family of them. So keep that in mind. The next family, that's kind of a parallel brother or sister to the Series IO, is the new Series 70, which is going to be available in August of 2013. And this model is similar in that you can see it's 500 millimeter, 2, 4, and 6 meter sensing ranges. So same as the Series IO, but it's potentiometer configurable. So it's got a little screwdriver twist is all it takes to adjust the sensing range as opposed to a button. So it's a little simpler in that respect. You don't need to learn about holding buttons for a certain period of time and looking at LEDs blinking to toggle through modes. This one is a lot simpler to program. And it uses, instead of IO-Link, there's a specific program called UltraProg IR that will give you a lot of expanded parameter access. So you can change things like we discussed earlier with the sampling and the response time and things like that. But very nice software, very easy to use. And again, come to our intermediate and advanced trainings and you'll learn all about that stuff. But this type of product, it's dual PNP switch point. It's not push-pull. So only PNP, but you get 2 switch point outputs on the switch point type. And then there's an analog current and an analog voltage model separate that have switch point outputs as well. And to keep that, keep in mind, we've got up top of that first bullet 30 new models, whereas the Series IO, there's only 8. So one of the reasons there's 30 models is because you have a separate current and separate voltage version. And also you have these models with the remote transducers and the pivoting heads. So you can see those heads on the upper right-hand corner that kind of angle and pivot. Those are really nice for customers optimizing their alignment to the target. And those are not available in the Series IO. This is just a Series 70 item. So that concludes the overview of some of the basic models we have in our cylindrical design, the 12, 18, and 30 millimeter diameter versions. Now we're going to discuss some of the surface mount or the rectangular products, again moving from smallest sensing range to largest. The F77 series is our least expensive ultrasonic sensor. It's also got some nice high-end features, and it's also our smallest. So this is kind of like a miniature or matchbox housing that gives you switch point and continuous outputs. It's also in the same housing as our ML7 photo eye. So if a photo eye like an ML7 has issues with target color, reflectivity, the beam's too focused, needs a wider beam, a sensor like this, tiny little sensor, can fit right in the same area as a ML7 photo eye and do the job. Okay, so in keeping in stride with our discussion on smallest to largest, let's go straight to the largest. The largest surface mount or largest range surface mount product that Pepperl+Fuchs offers for ultrasonics is the F260 series. This offers a 34-foot sensing range, and it gives you independent analog and dual switch point outputs both in the same housing. A very high accuracy, and it's a very rugged design, so it's tough to get a feel in looking at that picture as to the size of it. But it weighs roughly 4 pounds, and it's around 6 inches diameter, 7 inches diameter. So it's very, very large product, and made for large, outdoor applications, looking at very wide bins, things like that. And maybe we'll see in a short bit some of the applications for it. The next sensor to discuss is our cube housing. This is a compact housing with, again, very high visibility LEDs on each corner of the bottom and the top rear of the sensing face. So very nice if you're at a distance away and you want to know what the status of the sensor is. You can see it, if it's mounted up high on top of a tank, you can see it from the floor level. The sensing head can rotate in any of 5 different positions, which is very nice. You can program it via the push buttons or pactware, NPN and PNP models, also analog and current current and voltage models. And it offers a retroreflective mode, which is kind of nice for detection of irregularly shaped objects. So we've kind of gone over the basic models of switch point, analog output, cylindrical housings, and surface mount housings. But there's a lot of other technologies and capabilities for ultrasonic sensors than just those simple rudimentary designs. One is a double sheet detection. So if you're in a paper feeding application, you want to know if there's a misfeed where two pieces of paper get fed through. You can do that with a special ultrasonic Thru-Beam model. Likewise, on a big paper roll, if there's a splice, you need to detect that splice and cut it out so it doesn't go into your finished product. That's something you can do ultrasonically as well with a special device. We also have versions that are high-pressure washdown immune that can be used in food and beverage applications where there's high-pressure cleaners and sanitizers and things. There's also chemically resistant models. If you're perhaps in a semiconductor environment where there's caustic acids and things that are made to eat away metal on circuit boards, we have Teflon-coated transducers and chemically resistant models for those environments. And also there's hazardous location models. So there's special models designed for use in areas where there might be combustible gases or dust in the area. Okay, this is going now to section 5 of our basic training for ultrasonics, and this is a quick look at application solving accessories. So we have right angle deflectors that will reduce the sensor mounting profile. So you can see on, I guess, middle left, if you thread a sensor through the through hole there and mount it, the sensor sound can go from the transducer and bank off that 45-degree angle and then go out to look at a target. So you can get kind of a periscope effect with your ultrasonic sensor. There's also the push-button programming tools that we discussed earlier. I saw that UB-Prog 2 that can be used with the cylindrical models. There's various alignment aids and brackets and digital displays even. So quite a few different accessories are available to make ultrasonics even more applicable for sensing applications. Now we go into our sixth and final section, a little bit about the applications where ultrasonic sensors can be used. You can see in the application on the right, there's a sensor mounted beneath this loop of sheet metal. And that height of the sheet metal with respect to the sensing area, how high, how low it is directly proportional to the tension on that feed. So you want the optimum amount of tension that you don't pull too hard or have it too loose and things sag. You want a nice level of tension for stamping consistent parts. So the feedback from the ultrasonic sensor, this is an analog model, ensured that you got proper feed tension and you could adjust on the fly if things get a little too tight, a little too slack. That's what the sensor does, is it allows the controller to know that and adjust. The environment was originally going to be for a photo eye. You can see that down. You see a sensor mounted in that right angle bracket. That's an ultrasonic. And then to the right of it is a photo eye. But the oils and the dirt that came off of the sheet metal caused problems for the photo eye. It just got you were constantly cleaning the lens. So the right angle transducer allowed that ultrasonic to fit in that little trough there and basically take up about the same mounting height as the photo eye did. So that was roll loop control in a metal stamping application. Another popular ultrasonic application, whether it's rolls of paper or rolls of sheet metal, is to get roll diameter feedback, so you know when you're getting to the end of your roll. Again, continuous analog feedback is preferred, and the nice things with the ultrasonic sensors, they aren't affected by paper dust, they aren't affected by changing target color. I mentioned they're good for sheet metal, and in the previous application we said they're good for oils and dirt and dust and contaminants, all that stuff. So they're a great product for roll diameter feedback. Well, this is kind of a neat application for an ultrasonic, and this is for a company that makes conveyors that fill giant yards with piles of gravel and crushed asphalt and things like that. And they had originally used a limit switch, a mechanical sensor that hung from the top of the belt. But that sensor got hit with rocks, it stuck, it broke. It was a pretty violent application. So they decided to try a UC4000 ultrasonic sensor, which gave them about 15 feet of sensing range that they required. And it was able to look at this gravel, we mentioned before, hard stuff, gravel, things like that are great targets for ultrasonics. And this sensor worked great. And they could tuck it up inside where it was hidden, so it's not going to get hit by rocks and things like that. So it was just a nice device, and they know once the level of that stuff that's flying off the conveyor gets so high, it's time to swing that conveyor left or right and start creating another pile. So again, nice outdoor application for an ultrasonic, and it replaced a mechanical switch. I think the quintessential application for ultrasonic sensors is level control. So you see that in small tanks, big tanks, corn to beer to whatever. This particular tank required, it was a little bit caustic on the inside, so they wanted a Teflon film. So this sensor had a Teflon film, one of our UC2000 sensors, and gave the customer continuous level feedback, and it's fitted into a flange that goes into the top of the tank. Here's an application I alluded to a little bit earlier, but it's for ultrasonics on a crop sprayer. So as crops are needing to be fertilized or watered, pesticides applied, things like that, not all of the surfaces of the ground or the contours of the ground are smooth. You'll see plenty of corn and things like that planted in areas where maybe they're on the side of a mountain or something like that, a side of a hill. So as these sprayers go out, you don't want them running into the hill. So these sensors will sense the top of the crop, some of them will sense the ground, and they will move the arms automatically up and down so that there's no collisions. And also to make sure that there's an even spray applied to the whole area. It's not concentrated on one spot because the boom may be too low. It also is very nice because it optimizes the production of the farmer, because he can fly without having to manually look and lift and move stuff. The sensors take care of all that. So he's able to finish his job quicker because the sensors will take care of a lot of what he used to do by just having to use his eyes and manually shift the booms up and down. Crane position feedback in these big open areas, like this particular crane is picking up rocks and dumping them, and you get giant plumes of dust that come up. In areas like that, if you want to position the crane as it moves back and forth, is very difficult to do with a photo eye. The area is just way too dusty. So this is something, again, I think this application was solved with one of the F260 devices. But it just lets you know as the crane, you can do level control with it if you want to see if the levels of the aggregate below. But it's more for the cranes going forwards and backwards along those tracks as they pick up and dump off the crushed stones. Looking at the level of grains, again, another level application, but you can see here the customer, as things get dumped from the top, they didn't want the sensor to get beaten up, so they put this protective cover on it, and that allowed the sensor to look through the opening in the bottom to detect the level, but not get pelted by the things that are dropping from above. Another application that's great for ultrasonics is the monitoring of wood chips, whether it's the height of the pile or just the presence of them on a conveyor. Wood chips can be of dramatically different colors, wetnesses. They can be very dusty. The environments, the target surface can be slanted, and piles are flat. So all of that stuff plays into ultrasonics being a perfect sensor to detect and monitor levels and positions of wood chips. On forklifts, you want to have something that you can tuck nicely inside the framing of a forklift if you want to look and see if a pallet is present or if the forks are fully inserted into that pallet. So an ultrasonic can gauge that distance from the pallet, from the forklift to the pallet. And that nice little cube-style housing tucks nicely in there. It doesn't have nearly the depth that a mounting depth of a cylindrical. So that's an application where the rectangular style or surface mount style is a big benefit over a cylindrical. Okay, we'll come to near completion of our application section here. This is another application where, being like the forklift, where that cube housing can nicely kind of tuck in inside something. Here, this is a garbage can, residential garbage can pickup application, where the sensor will detect with dual switch point. It can tell those claws, okay, you're getting close to the garbage can. Okay, now it's in the window where you can close to pick it up, lift, and dump the contents. So again, the space-saving cube design is really nice for an ultrasonic sensor.